Hello friends, how are you? I hope that you all are good and doing well. Most of all, you are studying properly. Today in this video lecture, we will be discussing about the principle of mathematical induction. Before going into detail of this principle of mathematical induction, we will discuss something that will help you to understand this topic very easily. So friends, you must be aware of the thing that we generally what we do, that if we are given some facts, then we generalize the things that if this is true, then that may be true. Okay, so if we are given number of facts, number of statements, we can deduce some specific statement, we can find out the inference result that this may be true. Similarly, if we know that this fact is true and the second random fact is true, then we try to find out the general solution of anything. So in the mathematical way, what we do by the principle of mathematical induction, we try to solve the day-to-day life problem by using this tool. Laplace have told that analysis and natural philosophy owe their most important discoveries to the principle of mathematical induction. Newton was also indebted to it for his theory of the binomial and the principle of universal gravity. That means this mathematical tool is very useful in the scientific as well as the day-to-day life solving problems. So in this video lecture, we will properly discuss in detail and will solve the examples that how can we utilize the principle of mathematical induction. Okay friends, so friends, myself Virendra Kumar and you are watching Sciacademy channel. So let's start the video lecture. On key basis of mathematical thinking is deductive reasoning. And informal, for example, let us take three statements. Socrates is a man, all men are mortal, therefore we deduce that Socrates is mortal. So we were given two statements. First, that Socrates is a man and all men are mortal. So we find the specific statement that Socrates is a mortal. So that means we deduce with the help of the two statements a result, that is Socrates is mortal. So this type of activity is known as the mathematical deduction. To make this simple mathematical example, we could write that 8 is divisible by 2. So this statement, any number divisible by 2 is an even number. Second statement, so we deduce with the help of these two statements that 8 is an even number. So if the two statements are true, with the help of these two statements we deduce a particular statement that 8 is an even number. Thus, deduction in a nutshell is a statement to be proven, often called the theorems or conjecture. Valid deductive steps are derived and a proof may or may not be established. That is, deduction is the application of general case to a particular case. That means if we are given the general statements, so with the help of these general statements we can deduce a particular statements. As I told in the above two examples, that Socrates is a man and all men are mortal, therefore Socrates also a mortal. And in the second example, 8 is divisible by 2 and also and any number divisible by 2 are even number, therefore 8 is an even number. So this type of reasoning comes under the deduction. So what is induction? So induction is the reverse of the deduction. In case of deduction, we find out the particular case with the help of the general. But in case of induction, with the help of particular, we generalize the thing. Okay, we solve the problem. Firstly, what we'll do, we try to prove the case for particular thing, and next we try to solve the problem for the random thing, and then finally we conclude that this is generalized for the case. Okay, so here it is written in the NCERT textbook. Friends, I am here using the textbook directly because I want to teach you that how you can study the NCERT textbook and how can you utilize the concepts given in the NCERT textbook, how can you read the NCERT and learn from it directly without much trouble, without much coaching from other. So try to learn the things directly from the NCERT textbook, because in the NCERT textbooks it is given very well and the things are given very crystal clear. Just what you have to do, you have to learn the things how to study the textbooks. Okay, so in contrast to deduction, inductive reasoning depends on working with each case and developing a conjecture by observing incidences till we observe each and every case. Okay, so it is frequently used in mathematics and it is a key aspect of scientific reasoning, where collecting and analyzing data is the usual thing. Thus, in simple language, we can say the word induction means the generalization from a particular cases or facts. Okay, so in case of induction, we generalize things from the particular thing, while in the case of deduction, we find out the particular facts or cases or inference with the help of the general statements. Now we'll take very interesting case. Here in this figure 4.1, you can see that there are number of tiles arranged in a row one by one, and we use a form of complete induction called mathematical induction to understand the basic principle of how by flicking one tile cause to fall other tiles which are placed before the first tile, right? So this is the case of induction, because we assure that if first tile falls and the next tiles is happen to fall by the falling of first tile and any another tiles also, we check it that if any another tile is happen to fall because of these two tiles, then we can generalize that whole tiles may be falling because of just flicking the first tiles. So this is the case of induction. So let us study this case. When the first tile is pushed in the indicated direction, all the tiles will fall. How to be absolutely sure that all the tiles will fall? It is sufficient to know that first the first tile falls. Second case, in the event that any tile falls, its successor necessarily falls. That means in the first case, if first tile falls, it is necessary that second tiles should also fall, so that the successor tiles happen to fall one by one. So this is the underlying principle of mathematical induction. Induction is the word which is coming from the induce. That means one event is inducing the other event to happen, right? So we now know that the set of natural numbers n is a special ordered subset of the real numbers, because real numbers is including the natural numbers, okay, rational number, irrational numbers, all those things. Therefore natural number n is the subset of the real number, okay. In fact, n is the smallest subset of this real number with the following property. So a set S is said to be an inductive set if 1 belongs to S and x plus 1 also belongs to S whenever x belongs to S. Because if 1 is belonging to S and x plus 1 is also belonging to S, this implies that x is belonging to S. Since n is the smallest subset of R, which is an inductive set, it follows that any subset of R that is inductive set must contain n. So this is also an example of the mathematical induction. Now let us take another example, that we want to get the summation of many natural numbers. Many means here 20, 30, 50, 100, 200, 500, 1000, 10,000, lakhs. Any number of natural numbers can be summed up, and we want to find the final result. So is it possible to add all those numbers one by one and getting the result? No, it is not a simple thing. It is tedious. It may be cumbersome if we start summing one number by another number and adding up going on. No, it is not simple. So how can we do the sum of numbers 1, 2, 3, 4, so on? So there are two ways, but one that you will learn that if want to sum 1 plus 2 plus 3 plus 4 plus some n numbers, then you can and if you suppose that this sum is S, and if you write in the reverse order n plus n minus 1 plus n minus 2 plus so on plus 1, and you summed up, then 2s is equal to n plus 1 plus n plus 1 and n plus 1. This may be up to n terms, and that means total sum is n times n plus 1. Therefore s is equal to what? S is equal to n into n plus 1 divided by 2. So this is the result. But here we will do the sum by the help of mathematical induction. Okay, so let us see how we can do that. So firstly, what you will do, that you will try to check whether the sum is true for particular number 1 or not. So we have to get this solution 1 plus 2 plus 3 plus up to n. And also I would like to mention that in the LHS the terms are 1 plus 2 plus 3 up to n. So here LHS side n represent the number of terms, and in the RHS side n represents the value, that means n value. If we take 5 terms, so here in the RHS n will be 5. Okay, so what you will do, we will check for n is equal to 1. So if you put n is equal to 1, obviously 1 into 1 plus 1 divided by 2 is equal to 1. If we take n is equal to 2, that is 1 plus 2, that means 3, and we put this value here, 1 into 2 plus 1 divided by 2, that is 2 into 2 plus 1 divided by 2, that means 3. So we see that this is true for n is equal to 1, n is equal to 2, and n is equal to 3, and we can prove that this is true for n is equal to 4, and so on. And suppose that in some manner we are led to believe that this is correct formula. Okay, but how can this formula actually be proved? We want to prove this. So one method I have shown here that you can take the sum s is equal to 1 plus 2 plus 3 plus up to n, and you take the reverse order n plus n minus 1 plus n minus 2 plus up to 1, and add these two series and you will get the result. But another method is the mathematical induction, and we will use the principle of mathematical induction to prove this, that summation of the n natural numbers will be given by n into n plus 1 by 2. So what is the principle of mathematical induction? That is PMI. What is the principle of mathematical induction? So suppose there is a given statement Pn involving the natural number n such that, friend, you note that this is the statement for principle of mathematical induction. So you are given a statement Pn involving the natural number n such that first statement is that the statement is true for n is equal to 1, that is P at value n is equal to 1 is true. Okay, now second, if the statement is true for some random number n is equal to k, where k is some positive integer, then the statement is also true for n is equal to k plus 1. That is, the truth of p k implies that the truth of p k plus 1. What does it mean? This means that statement first tells that if for n is equal to 1, P1 is true. There is no if, this is given, that is certain. The statement 1 is true for n is equal to 1. The second supposition is that if, the condition is if the statement is true for any random number n is equal to k, then the statement may also be true for n is equal to k plus 1. And if this happens, then Pn is true for all natural number n. Okay friends, so this is the principle of mathematical induction, that will check that whether the statement given true for n is equal to 1. If it is true, then the statement would be possible that it is true for random number n is equal to k, and if it happens to be true, then it must be true for k plus 1. And if it is true for k plus 1 also, then we can generalize that the statement is true for any natural number n. Okay, so in solving the numerical, what you will do? Firstly, you will check for n is equal to 1. If it is true, then we will proceed further. That if it is true for random n is equal to k, and that leads to let's say that it is true for n is equal to k plus 1, then we can generalize that it is true for all the natural numbers n. So property 1 is simply a statement of the fact. Okay, it is a statement of the fact. There may be situations when a statement is true for all n is greater than equal to 4. In this case, state 1 will start from n is equal to 4. And we shall verify the result for n is equal to 4, that is 3 and 4. That means it is possible that situation starts from not n is equal to 1, but situation emphasize that the case is true for n is equal to 4. Then we will start further from the n is equal to 4. Okay. Now the second property is the conditional property, right? So this is first, this is second. So first is a simply statement of the fact. Second is the conditional property, that it doesn't assert that given statement is true for n is equal to k, but only that if it is true for n is equal to k, then it is also true for n is equal to k plus 1, right? That means second conditional property we have to check. It is not telling that it is true for n is equal to k. We will check it. If it is true for any random n is equal to k, then it implies that it is true for n is equal to k plus 1. And if so it happen, then we can conclude that it is true for n. If this statement is true for n is equal to k, then it is true for n is equal to k plus 1, and this is sometimes referred to as the inductive step. So this is also a inductive step. So the assumption that the given statement is true for n is equal to k in this inductive step is called the inductive hypothesis. Okay. Now let us take the example that sum of the odd natural number is equal to the square of the natural numbers. So sum of first 8 in odd natural number is the square of n. That is 1 plus 3 plus 5 plus 7 plus dash dash plus 2n minus 1 is equal square of the natural number n, where n is the number of terms. Now let us prove that this is true or not. So to prove that, first we will check that it is true for n is equal to 1. So as we put n is equal to 1 in this LHS, then it becomes 1 is equal to 1 square, that is equal to 1. So P1 is true for n is equal to 1. Now the next step is the inductive step, that we will prove this for some random n is equal to k, integer or natural number. So now after that we will prove that this is true for k plus 1. Suppose that pk is true for some positive integer k, then we need to prove that it is true for pk plus 1. That is, since pk is true, we have 1 plus 3 plus 5 plus 7 plus 2k minus 1 is equal to k square. Now consider that it is true. Now we have to prove that this is true for k plus 1. So we will keep k is equal to k plus 1 in the above equation. So this will become 1 plus 3 plus 5 plus 7 plus dash dash 2k minus 1 plus 2k plus 1 minus 1. That is equal to k square k plus 1 whole square, that means k square. Now let us take the example number 1. For all natural number n greater than equal to 1, prove that 1 square plus 2 square plus 3 square plus 4 square plus dash dash plus n square is equal to n into n plus 1 to n plus 1 by 6. So we have to prove by this mathematical induction. So let us take the LHS. So LHS is equal to 1 square plus 2 square plus 3 square plus 4 square plus dash dash plus n square. And by the principle of mathematical induction, first step we will apply, that is, let us check that it is true for n is equal to 1. That is, P1 is equal to we will find the P at n is equal to 1. So after substituting for n is equal to 1, we get that 1 into 1 plus 1 into 2 into 1 plus 1, that gives 1 into 2 into 3 divided by 6 is equal to 1. That means it is true for n is equal to 1. The first statement is true. Now we will check that whether it is true for n is equal to k or not. So assume that pk is true for some positive integer k. That is, let us check. We will put n is equal to k. So 1 square plus 2 square plus 3 square plus 4 square plus dash dash plus k square is equal to k into k plus 1 2k in plus 1 divided by 6. We shall now prove that it is true for n is equal to k plus 1. When it is true for k plus 1 also, then we can prove that this is true. So let us substitute n is equal to k plus 1. So therefore we get 1 square plus 2 square plus 3 square plus dash dash plus k square plus k plus 1 whole square, and up to this it is equal to k into k plus 1 into 2k plus 1 divided by 6 plus this k square, k plus 1 square. Now after simplification we get this by after taking LCM we get this Now this, so after simplification we get k plus 1 into k plus 1 plus 1 into 2k plus 1 plus 1, that is this value. So we see that this is in the form of n plus 1, n into n plus 1 to n plus 1. So this we take as a single value. So this we see that n into n plus 1 into 2n plus 1 plus 1 by 6. That is, this is true for n is equal to k plus 1 whenever this is true for n is equal to k. Hence, from the principle of mathematical induction, the statement Pn is true for all natural numbers n. So ultimately what we have to do is that we will check for n is equal to 1, and if it is true then we will assume that it is true for n is equal to k, and after that we will check whether it is true for n is equal to k plus 1 or not. If it is true for n is equal to k plus 1, then we will generalize that the statement is true for all natural numbers n. Now let us take the example number 2. Prove that for 2 to the power n greater than n for all positive integers n. So we have to prove this. 2 to the power n is greater than n. So we will check it for n is equal to 1. After substituting n is equal to 1, we see that 2 to the power 1 is greater than 1. That is obvious. Therefore P1 is true. Now we will assume that it is true for n is equal to k. So 2 to the power k is equal to k is greater than k. Now we will check that whether it is true for k plus 1 or not. So let n is equal to k plus 1. So that can be written as 2 to the power k plus 1 is equal to 2 to the power k into 2. That is this. Now we see that 2 into 2 to the power k is greater than 2k. We know that 2k is greater than k. Therefore we can write 2 into 2 to the power k plus 1 is greater than 2k. That is equal to k plus k, that is greater than equal to k plus 1. Okay, so we see that the state 2 to the power n is greater than n. Okay. Therefore pk plus 1 is true when pk is true. Hence, by principle of mathematical induction, it is proved that for every positive integer n, 2 to the power n is greater than n. Similarly, you can prove that for all natural number n greater than equal to 1, 1 by 1 dot 2 plus 1 by 2 dot 3 plus 1 by 3 dot 4 plus dash dash divide 1 by n into n plus 1 is given by n divided by n plus 1. So we will prove this by the principle of mathematical induction. For that we will take n is equal to 1 and we will check whether it is true for n is equal to 1 or not. So let us assume that this is Pn is equal to 1 by 1 dot 2 plus 1 by 2 dot 3 and so on. So now substitute n is equal to 1, then we get that 1 by 1 dot 2 is equal to 1 by 2 and that is equal to 1 by 1 plus 1. That is, it is true for n is equal to 1. Now let us assume that pk is true for some natural number k. That is this. Now we will prove that it is true for n is equal to k plus 1. So we will put n is equal to k plus 1 in Pn. So we will get this 1 by 1 dot p plus 1 by 1 dot 2 dot 3 plus 1 by 3 dot 4 plus up to this, and plus next 1 by k plus 1 into k plus 2. So how this is happening? So we have written, because this 1 by k plus 1 into k plus 1 plus 1, then this. Okay, now up to this value nothing but this is k by k plus 1. So this is k by k plus 1 and plus 1 by k plus 1 into k plus 2. Now after simplification by taking LCM, k plus 1 into k plus 2, and this becomes k into k plus 2 plus 1, and that is equal to k square plus 2k plus 1 divided by k plus 1 into k plus 2, and we know that this is nothing but k plus 1 whole square. So k plus 1 whole square divided by k plus 1 into k plus 2, that is equal to k plus 1 divided by k plus 2, that is nothing but k plus 1 divided by k plus 1 plus 1. So we see that pk plus 1 is true whenever pk is true. Hence, by the principle of mathematical induction, Pn is true for all natural numbers. So friends, we will use the principle of mathematical induction to solve such type of problems. Now let us take the example number 4. For every positive integer n, prove that 7 to the power n minus 3 to the power n is divisible by 4. So we'll assume that this is equal to, this is the statement Pn, 7 to the power n minus 3 to the power n is divisible by 4. Now we'll check that whether it is true for n is equal to 1 or not. So let us substitute n is equal to 1. We get that 7 to the power 1 minus 3 to the power 1 is equal to 4, which is obviously divisible by 4. So that is Pn is true for n is equal to 1. Now let us assume that it is true for n is equal to k. So this is 7 to the power k minus 3 to the power k is divisible by 4. This is the assumption. Now we will prove that whether it is true for n is equal to k plus 1 or not. So since it is divisible by 4, we can write this in terms of 4 into d for any d belonging to natural numbers. So now is to prove that this 7 to the power k plus 1 minus 3 to the power k plus 1, that can be written as 7 to the power k plus 1 minus 3 to the power k plus 1. We will write this step minus 7 dot 3 to the power k plus 7 dot 3 to the power k. Okay, so that to simplify, let us take common 7 into 7 to the power k minus 3 to the power k, and let us take here 3 to the power k common, so 7 minus 3. So ultimately what we will get, that 7 minus 3 is, so this, since we have assumed that this is true for pk, so we will take 7 to the power k minus 3 to the power k as equal to 4 into d, and this 7 minus 3 is equal to 4 into 3 to the power k. Therefore 4 is common out, 4 into 7d plus 3 to the power k. Now we see that this is multiple of 4, that is 7 to the power k plus 1 minus 3 to the power k plus 1 is divisible by 4 whenever it is true for k n is equal to k. That is, if pk is true, then it is also true for n is equal to k plus 1. Therefore, we prove that by the help of principle of mathematical induction, the statement given is true for every positive integer n. Now, let us solve the example number 5. Prove that 1 plus x to the power n is greater than equal to 1 plus nx. For all natural number n, where x is greater than minus 1. So condition is that x is always greater than minus 1. It is not equal to or minus 1, otherwise it is not valid. So let us Pn be the given statement. So Pn colon 1 plus x to the power n is greater than equal to 1 plus nx for all x greater than minus 1. So we will check for n is equal to 1. So Pn is true when n is equal to 1, that because since 1 plus x to the power 1 is equal to greater than 1 plus x, 1 dot x is equal to 1 plus x. So it is true for n is equal to 1, that is P1 is true. Now assume that it is true for n is equal to k, therefore we will put n is equal to k in the statement. So pk is equal to 1 plus x to the power k greater than and equal to 1 plus kx when x is greater than minus 1. So we assume that. Now we will prove that it is true for n is equal to k plus 1. When it is proved, then we can say that it is true for all the integers n. So let us consider the identity for n is equal to k plus 1. So 1 plus x to the power k plus 1 can be written as 1 plus x to the power k into 1 plus x to the power 1, and we know that 1 plus x to the power k can be 1 plus x to the power k can be written as greater than equal to 1 plus kx, because we have assumed that. Okay, so we have 1 plus x to the power k plus 1 greater than 1 plus kx into 1 plus x, right? We are using this identity. So now we can write that 1 plus x plus kx square. Now you can see that for where k is a natural number and x square is greater than equal to 0, so that kx square is equal to and greater than 0. Therefore we can write that 1 plus x plus kx square is greater than and equal to 1 plus x plus kx square kx. So that means this is always greater than this. So we obtain that 1 plus x to the power k plus 1 is greater than 1 plus x plus kx. That is 1 plus x to the power k plus 1 is greater than equal to 1 plus, taking x common out, 1 plus k into x. So it is established that statement into is true. So that is, it is true for n is equal to k plus 1. So what we use this in this example, this condition here, k is a natural number and x square is greater than equal to 0, because x is greater than minus 1, Therefore, x square is greater than equal to 0. So that kx square always be greater than equal to 0. Therefore, we solve this by the principle of mathematical induction, that is Pn statement is true for all natural numbers. Now let us solve the example 6. Prove that the statement 2.7 to the power n plus 3.5 to the power n minus 5 is divisible by 24 for all natural number small n. So let the statement given is Pn, then Pn colon is 2.7 to the power n plus 3.5 to the power n minus 5, and it is divisible by 24. So now we'll prove that whether it is true for P1 or not, that is it is true for n is equal to 1 or not. So let us put n is equal to 1 in the statement. We see that 2.7 to the power 1 plus 3.5 to the power 1 minus 5 is equal to 14 plus 15 minus 5 is equal to 24. So we get the 24, that is obviously divisible by 24. Now we will assume that it is true for n is equal to k, that is pk is true. So we will substitute that 2.7 to the power k plus 3.5 to the power k minus 5 is equal to 24 cube, that is it is divisible by 24 where k is any natural number. Now we will prove that whether it is true for n is equal to k plus 1 or not. So let us substitute n is equal to k plus 1 in the statement. Then we get 2.7 to the power k plus 1 plus 3.5 to the power k plus 1 minus 5, and that can be written as 2.7 to the power k into 7 plus 3.5 to the power k into 5 minus 5. Now let us take 7 common out. 2.7 to the power k plus 3.5 to the power k minus 5. So what we have done here, that we just added this and subtracted this also to simplify the problem. So you should note that to simplify such type of problem, we have in the previous example also we have done the addition and subtraction of the same type of number. So here, so that we can take the 7 common out, we subtracted and added the same quantity, so that we can take 7 common out. 2.7 to the power k plus 3.5 to the power k minus 5 minus 3.5 to the power k plus 5. Now this we have assumed that we have to take this into consideration. So we 2.7 to the power k plus 3.5 to the power k minus 5, this quantity is nothing but this minus 3.5 to the power k plus 5. After simplification we get that this plus this, and that ultimately gives the value of 7 into 24 q minus 6.5 to the power k plus 30. Therefore we can write this as in this term by taking 6 common out. So we can write this as this, by 5 to the power k minus 5 is always multiple of 4. Thus, since 5 to the power k minus 5 is multiple of 4, so we can write that 5 to the power k minus 5 is equal to 4p. So ultimately we have this. So taking 24 common out, we get 7q minus p. So this is some number that can be written as r. So we see that the statement is true for n is equal to k plus 1. Therefore the statement is divisible by 24 for n is equal to k plus 1, that is pk plus 1 is true whenever pk is true. Hence, by the principle of mathematical induction, it is said that Pn is true for all natural numbers.